All right, so let's talk about a couple of things. So first of all, hopefully everybody had decent R&R days on Tuesday and Wednesday. I had my COVID shot on Tuesday, so shot number 1's down and I'm fine from it. I had an 8-hour drive yesterday, so it was that's why I'm doing my classes online. I only have one class today. I'm doing it online mostly because I just wanted to sleep in a little bit. So is what it is. I'm not sick or anything. So let's talk. We'll go ahead and go through the homework assignment here in a few minutes, but let's start off by talking about the midterm a little bit and what to expect and when it's going to be and what might be on it and all that jazz. So let's go here. All right, so my plan is to have the midterm be next Thursday, so a week from today. So Thursday, 3/18. It'll be an online Blackboard exam. And I'm going to actually try to get them all graded that day if possible, because I think I have to have midterm grades turned in by end of day that following Friday, the very next day. But I'll do my best for that. But that'll be next Thursday during our class time. Exam will be designed to take about an hour. We'll have 10 questions. There will be at least one conversion question as usual. So probably something like converting a value from, base 2 to, base 16 or something like that. It could also be converting a size like in kilobytes into megabits, something like that. So, these are your kind of stock. I'm a computer science major. I should understand those things inside and out, no matter what class I'm in. There'll be one question dealing with that type of thing. So make sure that you've refreshed those things. Hopefully you're far enough in now where you won't even need to review. You just know that the scalar between bits and bytes is 8. And the multiplier is 1024 as you go up each of those lists. So, 1 bit, well, a kilobit is 1024 bits, a megabit is 1024 kilobits, so on and so forth. A byte is 8 bits. A kilobyte is 1024 bytes. Okay, so then the rest of the exam is going to focus on the things we've talked about so far this semester. Now, the exam is going to be more focused on the data structure stuff than it is on C++. So I'll ask you to write C++ code as like the coding examples, and it would be fair game to ask some stuff about pointers and things like that, since that is new material for this semester where you really haven't had to deal with special syntaxes for pointers. So you'll be, I will assume you will know how to follow that stuff. But I'm not going to test you over like how to write a for loop in C++. I'm just going to assume that you can do that. And when you write the code on the exam, the assumption is that the code is being written, without testing it. So I'll take that into consideration if you miss a semicolon here and there, or, make a little syntax error or a small logic error, that it's clear you were thinking down the right path, but just in an exam situation didn't come up with the ideal answer or something like that. So the usual, give me C++ based as close to working code as you can come up with, and I'll read between the lines for the rest of it. So having said that, let's just go and flip through the slides up to this point. So I can kind of point out where I think are, the areas where you should focus when you're studying for the exam. The exam will be closed book, closed note, but it will be online. I obviously can't keep you from, looking stuff up and things like that. All I'm saying is you're doing yourself a disservice if you do that, because you won't know what you've learned and what you haven't learned. Remember, I still have the policy where if you do better on the final exam than you did on the midterm, I'll replace your midterm exam score with whatever you got in the final exam. Okay, so as we go through here, I mean, you should have a good idea of where C++ fits in the evolution of our languages, but that's not something I'm going to really ask you a question about. So I wouldn't worry about that. Similarly, we've been dealing with compilers for a year now, so you should certainly know what a compiler is. You should certainly know about its role, but I'm probably not going to be asking you specific questions about compilers. If anything, I might say that there's going to be a higher expectation of programming competence on this exam than in previous programming exams you've had, just because this is your third semester of computer programming. So, where maybe in the past they may have asked 3 or 4 programming questions on an exam, maybe I would ask more like 4 or 5 on this exam, not necessarily geared at being hard questions that would take you a long time to answer, but more not allowing you to hide from programming incompetence with short answer questions. Because like in the past, sometimes, it's pretty clear to see that you might have somebody who gets a 60% in the exam where they pretty much knew the theory information, but left all the programming questions blank. We're getting to the point now as third semester computer programmers that you really can't just be leaving programming questions blank. So that's going to have consequences when it comes to the grade. So make sure you're going through and practicing programming stuff, things that we've done in class and things related to the homework assignments and things like that. All right, won't ask you anything about that. The role of header files, that could make it as a question on there. I think this idea of, because that's kind of related to the compilers, the idea of a header file being kind of your interface for your implementation files, where it used to be done maybe as a prototype function at the top of the implementation file, and now you pull it all into a header file and embed it at the top of your code. That allows your code to be a little bit more self-documenting, more organized, things like that. So it probably wouldn't be any sort of deep question about that. It might even be something as easy as, assume you have to write these 3 functions, show me just what the header file looks like. So in that case, it's kind of a programming-esque question where I'm asking you to effectively show me that you know how to write the headers for 3 or 4 functions that, with the correct return types and the correct parameters and things like that. But I'm not actually asking you to implement that. I'm just asking you to show me what the contents of a header file might look like. So make sure you do study that. I'm not saying that's 100% chance, but that would be a fair game type question. I probably will not cover anything with structs on the exam, mostly because we really haven't used them very much. We kind of talked about them as the gateway drug towards object-oriented C++, but I don't think we've really had concrete examples of a struct in practice. So something you should know about, something that really would be fair game to ask, but I doubt very much I'll ask you to write something with structs. It is possible that maybe I give you some code that uses a struct, and I might have 1 or 2 of those questions where I say, what does this code do? And you should be able to read code that has the use of a struct in it, which is kind of like dictionaries in Python. All right. Questions like this, like how big a char is in different languages. I mean, so far our experience has been that chars are 1 byte big in C++, specifically on Ubuntu, but that's not the kind of question I'm going to be asking. I could ask a question, about like, allocating memory or something, where I do something like, some number times the size of a char. And I ask you how many bytes that would be, assuming that a char size is 8 bits. I might say something like that. So then expect you to do the math where if I have, or size of a char is 1 byte. I would ask you to do the math, but I would give you that information. You wouldn't have to necessarily memorize what a char size is, even though that shouldn't be a big deal. That's not the thing I'm testing. I'm more testing on, that concept of pointers and size of memory addresses, and what the difference is between contiguous memory and non-contiguous memory, like we've started talking with our linear linked data structures, that kind of stuff. So this idea of how strings are stored with that \0, I think this is an important concept. Whether or not I'll directly test on this exact thing or not, you should have a concept that strings live in memory somewhere and are terminated by some sort of special character. And that's the historical nature of a string literal in C and C++. Even though in this class we are using more modern strings to make it mimic, Java a little bit better, since we're used to friendly strings in Java, and now we have pretty friendly strings in C++. So I'm not going to get into some like crazy questions about string literals in C++, but you should at least have an academic knowledge that there is a \0 string termination character in a string, and because all these things kind of relate to this idea of pointers and memory, bit spaces where we have, 160 bytes of memory and things live across those bytes and you might not use all of them. How do you know when the string ends, and that kind of stuff. So now we're probably hitting the meat of, really the stuff that I really am going to start caring about. If anything, I would say the theme of this midterm exam will be pointers and the beginning of linked lists, since we've just started getting into linear linked data structures. And really, the linked lists are just kind of our first, let's call it, traditional application of pointers. So if we were picking a theme for the first 8 weeks, besides kind of converting over to be a C++ programmer, it's really this idea of exposed memory, pointers, special syntax for working with pointers, that kind of stuff. So certainly be very familiar with that. That will appear on the exam in multiple ways. Okay, I'm not going to ask you history questions. I mean, again, the exam is going to be more of applied thing, so I don't want you to go through and memorize all this historical stuff. The historical stuff is more about kind of pulling you into a foundational understanding of how we got to where we are today. What I'm going to be testing you on is your competence in working with where we are today, not your ability to, remember back when 50, 60, 70, 80 years before you were born, things worked a certain way or something like that. You certainly should be able to write an error-free hello world program in C++. There's probably a pretty good chance that'll show up on there. I kind of like those kind of questions, not so much because, I want you to memorize something, but one of the things that hopefully I've instilled in you over the last 3 semesters of programming is this idea that, even though all programming languages are the same, you just have to, kind of convert to the different syntax and stuff. It is beneficial as a programmer to have that kind of that basic template of a hello world program in a specific language memorized, so that when you are asked to sit down and write something in a certain language, you can immediately give yourself a starting template. So that's something you should be able to write in Python now. It's something you should be able to write in Java, and now you should be able to write it in C++. So you should be able to create effectively an empty C++ program that all it does is print something to the screen, giving you a starting point for writing any more complicated C++ program. So I would say there's probably a fairly high chance that I'll ask you to write a completely working, error-free hello world program in C++. All right, this is what we were talking about header files and interfaces with Java. I don't think I'll ask you questions about interfaces from Java. I'll probably keep the focus on C++ and kind of the relationship to interfaces through header files. But I'll probably ask it more from the context of why do we need header files as opposed to how are header files kind of like Java interfaces. That's more of a chicken or the egg problem because Java came out much later than C++. So really, Java took that idea of an interface and said, you know, hey, sometimes we want to police the abilities that an object might have, and that's done through an interface where a header file doesn't do any policing. A header file exists for the compiler to make it its first pass and know about all the symbols it might run into, and then it happens to also benefit the human programmer to be able to glance at this header file that doesn't have all the implementation stuff in it and kind of see what stuff exists in the program. So they are serving different purposes, even though they maybe look a little similar. All right. Similar to this, design patterns, we reminded ourselves of that and kind of looked at header files as kind of like an MVC type of design pattern where we kind of keep our design in one place and our implementation in another place. Similar to what we talked about with Android last semester. I probably am not going, I mean, it's a little bit of a stretch to kind of talk about header files and the implementation files in C++ is fitting a design pattern because design patterns, this concept didn't exist when C++ came out. So it was kind of me trying to make a connection to something you'd already seen. So I doubt very much I'll ask you anything about design patterns on the exam. You should certainly be familiar with what they are, but I don't think we really have a good example of using them yet. So with C++, so I probably won't ask something about that. I probably will also not test over anything specific to Linux. It's an important skill. It's something that I do want you to be exposed to as a computer scientist because you are going to be working on different operating systems throughout your career. But in terms of the purpose of this class being a data structures class, at the end of the day, I don't necessarily care how much you've learned about Linux. I'm giving you the opportunity to learn about it by forcing you to do your homework within it. I also know that we had an issue with our virtual machine server that some of you brought to my attention, and I also was in talks with Blade, and I think they had a hard drive go down or something. So nothing was lost, but I think that was the functionality might have been sketch. So we're getting that fixed, but so if you're one of those people that are in those shoes, what you might do is if you don't have your own local copy of Linux or something, maybe in the short term, go and download Eclipse, the same thing we used last semester, and you do the C++ version of it. So you can at least work on your homework locally. I mean, in the ideal world, I want you to be getting experience working on Linux. But at the same time, I also don't want it to be a hindrance from you learning the data structure stuff from the class. So I guess I'm going to officially say now, and let's just say for the rest of the semester, if you are in a situation where you feel that working on your assignments through Linux is becoming a hindrance to the rest of your learning, go ahead and get yourself whatever local C++ environment you want set up. You can install Visual Studio. Visual Studio Express is free and it will support C++ and all the stuff we're doing in here. So whatever you want to do is fine. I'm strongly encouraging you to do this through Linux because I think it's a good experience for you to do, but if you feel that because of whatever limitations you're running into, it's problematic, let's make sure that you can focus on the data structures aspect of the class. So if you have questions about that, talk to me offline and we can look into alternatives, but I guess I'll officially give you permission for that at this point. All right, so we introduced this concept of data structures, and right now we're looking at the linear linked data structures. And we've looked at kind of a generic approach to them through linked lists, but we're also going to be looking at stacks and queues here pretty quickly. And stacks and queues are actually subsets of linked lists. So a stack has functions that allow you to add something to the front of the list and remove from the front of the list. So it's add front, remove front. Those are the only two functions that a stack supports. None of this add in, none of this add or remove in the middle, only from the front. So it's a simplified version of a linked list that follows the idea of a stack, where a stack is like a stack of magazines or a stack of cards, where it's a last in, first out thing, where you put things on top of a stack, and when you remove something from a stack, you remove it from the top of the stack. All right, so stacks aren't going to be this brand new, newfangled thing that we're learning. It's something that's been around that we already understand through linked lists. It's just a simplified version of a linked list. Similarly, queues you get in is like a line. You get into the end of the line, so it's add end, and you leave from the front of the line. It's remove front. So a queue only implements those two things, DQ and NQ. So they're simplified versions of what we've already looked at with our generic linked list. All right. So then after we cover those in the second half of the semester, we'll be looking at our nonlinear linked data structures with trees and things like that, which take a look, those will be kind of a new concept, but a similar concept. Just you don't have one node linked to exactly one other node. You might have it linked to multiple other nodes, creating something that's not a line, nonlinear, and now it's more of a tree structure or something like that. All right. Certainly understand the differences between arrays and linked lists. I will say this will be tested on at least one question, if not multiple questions. Understand that those dynamics around contiguous memory being required for arrays versus contiguous memory not being guaranteed for linked lists, and the pros and cons of that relative to speed and memory efficiency. So be able to ask questions or answer questions like, what's the difference between an array and a linked list? Or give me some example, or give me an example of something that a linked list would be the appropriate solution for, but an array would not. Something like that. So I want you to show that you can critically think about these two tools and when they are the right tool for the job. I want you to show me that you don't view linked lists as being the upgrade to arrays, because they're not. These are both viable tools that are used all the time in programs today, and they lend themselves to different kinds of problems. I'd be able to speak to those things about speed and memory efficiency and that kind of stuff. Certainly be able to write a generic object in C++. So if I give you so our example in class has been this card object, but if I, give you a scenario on the exam where, create an object capable of holding I'll just make something up, like a baseball player, where a player has a first name, a last name, a jersey number, and a batting average or something like that. Create that class and the appropriate constructor for it. Show me both the header file and the implementation file. So I want you to show me that your comfort level of working between those two things. I will say that on the exam, if it makes your life easier, this isn't a requirement, but if you want to put your answers up on like GitHub, if you want to have like a single repository and then just submit the link for each of your questions for that's okay. Whatever you're most comfortable with for getting your code into Blackboard. I can usually figure it out. I realize that Blackboard removes some indentation and stuff like that, which is obviously a bigger problem in like Python. Java and C++ don't care about indentation. My eyes do, but I could usually figure it out. I'm not going to be asking you to write hundreds of lines of code. So if you're perfectly happy just pasting it into Blackboard or something, that's fine as well. But whatever you think is the best way of submitting the code, you could even write it in Visual Studio Code and take a screenshot of the code and submit that as your answer or something. I think that would be adequate as well. All right.
Question for the programming questions that you're going to ask with like classes and stuff. Yep. Will you specify if we need to write like a header file or if we can just assume the header file?
Yeah, I will. I'll say if I expect you to include a header file as well.
All right,
so
cool,
let's make the assumption that I forget to do that. You turn something in and I take off points. If I didn't specifically ask for the header file, but I took off points for you putting it, I'll give you the points back. So my intention is if I want to see a header file, I'll ask you for one. Because there'll probably be at least one question where I only ask for the header file, where I don't ask for you to implement it. I just want to see that you know how to write the header file. So with that in mind, I might even split like the object question into two questions. Show me the header file for this guy, then show me the implementation file. Two separate questions, one focusing on the header, one focusing on the other part. Maybe it's related to the identical problem, maybe it's related to a different problem, but I'll probably split it like that rather than having you try to shove too much stuff into the answer box for one question. Let's see. There will be a question on there related to JSON, but not related to C++ and JSON, since we haven't gotten to processing JSON with C++ yet. And I'm actually still a little bit on the fence since I want to make sure we get into our nonlinear linked list. So I might actually just write the JSON interpreter or find one so that we just can build our objects rather than spend time writing the interpreter ourselves. I think a JSON interpreter is a worthwhile exercise, but I also need to make sure that we can fit everything in, since semester does end a week early since we had our fake spring break this week. So let me look at that, but at the very least, you should be familiar with what JSON is. If I ask you to write, like if I give you some information and I say, show me a JSON string that relates this information in some sort of structured way. Maybe I give you two baseball players and I just write it out. We have a baseball player, Mike Littman, age, whatever, blah, blah, blah. And I say, put these two players in a JSON array and show me what that format looks like. Some reasonable format for a JSON array for that. You should be able to do that. So you should know what JSON looks like, how it's organized. But at this point, from the specific, from the perspective of data being transmitted from one program to another program using JSON, not so much actually digesting the JSON yet, since we keep pausing that to go down the linked list path and things like that. So, the aspects that I would probably test over that are related to that is I might ask you to write some C++ functions that deal with string manipulation, things like that. That's effectively what we will or we're going to do related to JSON parsing, is we're manipulating strings. These are the same kinds of questions that I asked in Python and asked in Java, where, hey, these are generalistic, where's your current programming skill set? And the kinds of questions that I like asking that are kind of the right bite size for a exam question are, string manipulation type questions, or, write a function that takes a string as a parameter and, counts the number of spaces in the string, or reverses the string and converts all uppercase letters to lowercase and all lowercase letters to uppercase, stuff like that. Or write a function that called is palindrome or something that takes in a string and returns true if that string is a palindrome, that is to say that it is spelled the same way forward and backwards, that kind of stuff. So little string manipulation, problems that require you to create a couple of variables, write a loop or two, and write some if statements. Those are my way of drilling your current programming competency, not so much focusing on data structures, but really focusing on your ability to now wield C++ as a experienced programmer and see how you've grown from 200 to 250 to now 300. You should certainly be a better programmer now than you were in 200, even though you're wielding a different language. So keep in mind, there will be some programming questions on there that maybe have little to do with linked lists or pointers or even arrays. And it's just show me that you know how to program, do some string stuff or do some loop stuff or whatever. Maybe it's even looping through an array or something in C++. Okay. This stuff about like reading from the URL and things like that won't be on the test. It's interesting, it's good stuff, but typically when you need to do something like that, you'll go and look at a previous program you wrote or Google it or something like that. That's not what I'm testing on here. I'm looking at programming competency. All right, so this is where we start getting into our linked list stuff. So our first abstract data type we looked at was a linked list. I already mentioned stacks and queues today, which are subsets of linked lists. So you've actually already been introduced to all of it. But for this exam, we'll be focusing on just that generic idea of a linked list as opposed to an array and the differences between those guys. So you should certainly understand these concepts of a singly linked list where we have a node that has a payload that links to another node that has a payload, so on and so forth. We keep track of a head pointer. We may keep track of a tail pointer. Not all linked list implementations keep track of tail, but it is beneficial. It's just one more variable to keep track of. They might also keep track of the length. I think we called ours count. But regardless, this picture here, understanding that a linked list differs from an array in that it is not stored in contiguous memory. That node that holds the 4 there doesn't necessarily live right next to the 6th, the node that holds the 6 there in memory, even though it's depicted linearly here. Those two guys might become completely different neighborhoods in memory. And that little arrow going between them, that's the thing that links them together, that pointer that links the 4 to the 6. You have to travel along that pointer to get to the next node, which isn't just right next door necessarily. Yeah, so this slide, I would say, is pretty important. So to be able to answer any questions dealing with linked lists versus arrays, the differentiating factors there being, contiguous memory versus non-contiguous memory. So I would pay close attention to this slide. This slide kind of summarizes both sides. The delete function as it relates to pointers, I would say is fair game. I'm certainly not going to take off points on the exam if you write some good code and don't clean up your own mess at the end by deleting any pointer you created. But if I were to ask a question about what's the delete function and related to pointers and why would you use it, you should be able to kind of talk about that. We can't rely on automatic garbage collection in C++, and if we create new memory and we're done using that memory, it's our responsibility to then delete that memory. We should clean up our own messes. So understand the purpose this delete function. It's actually, I think, a very good example, or maybe even a reminder of how our programming languages really do mimic the way we solve problems in real life. I mean, in reality, the idea is, if my wife yells at me all the time, if I make a mess, I should be cleaning that mess up. You know, where I operate under the guise that there's an automatic garbage collection in the house, and it just kind of swings through and cleans everything up. We do have a robotic vacuum, so that's sort of kind of true for things that hit the floor. But you know, you get my point, is that programming languages do attempt to give us tools similar to the way we solve problems in real life. When we make a mess, we should clean it up. So our programming language has given us a delete tool that allows us to give back to the operating system memory when we're done using it. And that just seems like something that we should do as good programmers. It's something that we haven't been trained to do necessarily up to this point, because it's never been our responsibility. We've really been lazy problem solvers. We've been artificially lazy problem solvers over the last year, because the languages we've worked with had automatic garbage collection and took care of the messes for us, maybe lulling us into a feeling like, oh, it must not be important. Where really the reality is, it was so important that these languages decided that programmers had trouble doing it on their own, so we'll do it for them. But now we're in a situation where we can't necessarily rely on memory being cleaned up for us. So when we make a mess, we should clean that mess up. And now we actually get to think about that with a language like C++. So be familiar with the delete function. Like I said, I probably won't take off points if I'm not asking a question specifically about the delete function and you happen to be writing some code where the use of the delete function would be appropriate. I won't like take off points because you forgot to clean up your mess. I might remind you that you didn't clean up your mess or something like that, but you know, at the very least, I want this to be something that is, you know, on your radar as a programmer's responsibility, depending on the ecosystem you're working within. So this is more of our recent stuff when we're actually writing our linked list stuff. We talked about insertion sort last time, and I think this is where we ended up for the homework for today, was dealing with insertion sort on our linked list. All right, so that is kind of the what'll cover the exam. I will set aside some time on Tuesday if you have questions or want me to go over some specific examples in preparation for the exam. During class, I will. Otherwise, we'll look at the homework assignment that will be due on Tuesday. So try to prepare for the exam maybe for Tuesday, so you have any questions or things you want me to cover. But we'll actually have the exam during our class time on a week from today. And just like what I've done before, the exam's designed to be an hour. I'll put it up for the entirety of the class. I'll probably end up opening it just a little early and letting it close maybe 20 minutes late, just so we don't have, you know, weird lockout things. But it's not going to be something you'll have like a 4-hour window to work on. So hopefully it's not a time crunch thing where you run out of time to do the exam. If you do, that probably means you weren't prepared enough. But I'll be around and live during the exam. So if you have questions, I'll be on Slack and can certainly jump on a Zoom thing or something if you are just don't understand what's happening, or you can't get the exam opened, or whatever it is. So I'll be around, but we just won't meet for class because that day will be our exam day. All right, questions about the exam or any of that other crap? Okay, so let's go and let's look at our insertion sort for our linked list, where we were asked to perform the insertion sort sorting mechanism for our linked list, but not swapping payloads. We were actually, connecting up nodes and things like that. Not that you couldn't swap payloads. That was the conversation that we had this last time. Like, wouldn't it make sense just to swap payloads instead of, connecting nodes and things? The answer is, yeah, it could. Because a node itself is just a housing unit for a payload. And ultimately, if the goal is just to have everything in the right order, then, if we had two things that needed to live in different places, we could just swap the payloads. And that wouldn't be the end of the world, because one node is just as good as another node. It's not like some node is made of solid gold and another node is made of, aluminum or something. But, for this particular exercise, we said you can't just swap payloads. You actually have to manipulate pointers to get these things in different places in memory, with the understanding that right now we are practicing working with pointers. We want to put ourselves in that position of being uncomfortable, where kind of like we're floating in outer space, and we need to make sure that, the astronauts are all hooked to the ship so nobody goes and floats off or something like that. So that's kind of the problem we were looking at. So before I dive into this, were there any interesting challenges anybody bumped into on this homework assignment? Or was just
personally the hardest part was that, like, if you're swapping something that is the head and you don't, I don't really know how to explain it, but if you swap like the head, you need to point to the head, of course, which really messed everything up for a while. I don't really know what I exactly did to solve it.
Okay.
But that made it really complicated, because you had to do something different if it was the head versus if it was just two in the middle.
Right. So really something similar to like what we dealt with when we did like the add front, remove front, or added index, really actually probably more added index and remove an index, where we kind of had to treat the extremities of the list as somewhat special cases.
Yes.
Yeah, so certainly, yeah, and that's good that you were kind of challenged in that, because that is something we do need to consider. If we're swapping something at the beginning, well, things get a little bit more complex possibly, but also way more important, because the last thing we want to do is lose the front of the list, right? Because then you don't have access to any of the list if you mess up and the front of the list floats off into space. All right, so I would say that's a good challenge you bumped into. Anybody else have anything they want to report before we dive into this? I'll start loading my stuff over here. All right, we were rating this inside of LinkedList, right? All right, so here's our linked list class, and we're going to go ahead and say that we're going to teach a linked list how to sort itself, is the concept here, right? So we're going to go ahead and say it's going to return nothing. So we're going to put this in the header file. So we're returning no value because it's going to sort itself internally. We're going to call this insertion sort. It'll take no parameters because it's just going to do the magical insertion sort stuff. So I'll copy that and I'll open up linked list CPP, and we'll go ahead and I'll write this guy up here. So this is linked list. All right, so if you remember, insertion sort basically says we start off at bucket 1, if we're assuming this is like a 0 indexed array, and we try to move the element as close to the front of the list as possible, swapping along the way as long as it should move to the front of the list. All right, so let's get our basic structure down here, and hopefully it was helpful to draw some pictures. So if we even come back here and let's see, can I maybe steal a, maybe steal this one. Ugh. All right, so let's get my preview and doodad stuff disconnected here. All right, good. This is not in order. So we'll say here's a linked list that needs to be sorted. All right. So I'm going to rename a couple of these variables that kind of match up to variables that we've had before. So I think maybe we've called something like this is like cur start. And I always call this guy like the follower. All right, so when we start our voyage through here, cur start will start off at the second element in the list. All right, so we're only going to do any of this if our list has a size greater than 1, has a count greater than 1. Because if it has a count of 1 or less, it's already sorted, right? So if it has a count greater than 1, we're going to go ahead and set cur start up at bucket 1. We'll make the follower point to the same place, and then we'll start trying to move this guy further up in our list until we can get it where it needs to go. Now, hopefully one of the things that you recognized here is, you know, it would have been really nice if we had a doubly linked list here where we could actually get to the node that came right before me, because right now we don't have that, right? Right now what we have is a singly linked list where if I'm starting right here, the only way to get to the node before me is to start at the front of the list and run up to the node whose next node is the dude I'm currently pointing at, which means you got a lot of practice working with memory. All right, so I'm going to give myself some functions along the way, helper functions that are going to help me do some of this logic. All right, and we're going to do that as we kind of dive into this. So we're going to go ahead and we're going to start off with our loop. Potentially, we're going to go from bucket 1 all the way up to bucket count -1, trying to get everything to move as close to the front of the list as possible. So this is our core structure for an insertion sort. So I'm going to say for, well, I'm going to ask it more generically first. I'm going to say if this count is greater than 1, that means we have stuff to do. So really this asks the question, does this list need to potentially be sorted? So if the count is greater than 1, I'm only inside of this if statement if there's at least 2 elements in the list, which means that I know that there is a bucket 1. There might not be a bucket 2, but there's at least a bucket 1 and a bucket 0. So we're going to go ahead and give ourselves a couple of these pointers. So we're going to create a node pointer called cur start. And cur start is going to be equal to head's next node. It will point at the thing that head points to, that head's next node points to. That's this picture right here. So cur start will be heads get next node. That's what cur start's going to point to. Okay. Then we're going to have our follower. Follower is always going to get reset to the same thing as cur start when we go and do our thing. And how long does cur start do its thing? Cur start's going to do its thing as long as it is less than its position. So we might actually decide we want to keep track of another variable. We might call this cur start node, and then we might also have like a cur start position, which maybe starts off at 1 initially, because as we swap stuff, the positions are going to change. Okay, and just real quick here, I want to go look at my linked list, and actually I'll do this in the header file. Do I have a get at index? I do not. It would probably be helpful for me to go ahead and have the ability to get the node that lives at an index, because as I go through here, I'm going to pretty often want to get a node at a place, either the place where I'm currently at or the place that's right before me. So we're going to go ahead, and before we go even any farther here, we're going to write this guy. So we're going to create do we want to get the node? I'm going to make the argument here, just to add a little bit more knowledge into this. I'm going to put this under our private section, that getting a node at index is something that only needs to be done inside of the class. We don't want to expose that ability to things outside of this class. Maybe getting something at an index outside of this class would actually get the payload that lives at the index, not the node itself. The reason why we're going to want the nodes themselves here is because I want to be able to create a pointer that points to this whole node, where maybe somebody who's using my linked list and their implementation for something else, they might want to know, hey, give me the payload that lives at bucket 1. Give me the payload that lives at bucket 2, that type of thing. So maybe there would be a public function that only returns the payload, as opposed to the actual node, which is a memory address. So with that in mind, I'm going to put that in the private section here. So we're going to have a function that's going to return a node pointer called get node at index. And this will take in an int index as a parameter. And then we'll go ahead and put this in here. This is a node pointer, linked list, get node at index. Now we can do some error checking in here and make sure that the index they gave us is, we can say if index is well, let's do something like this. Let's say if this count is greater than 0 and index you know what? The error checking I'm doing here is really saying, is index potentially a legal thing? So we're going to say if index is greater than or equal to 0 and index is less than this count, then we'll potentially do something here. Technically, index being greater than or equal to 0 doesn't do enough, but since we use an and here, this will cover us if we say if index is less than count. If count is 0 and the index is 0, this will fail on this side because there is no buckets in there. All right, but only if index is a legal thing will we want to go ahead and return the node at that position in the list. And we can just do that with a for loop, right? So we can say node pointer cur node is equal to this head. We're only in this if statement if we actually have a legal index we're chasing. So then we'll say for int I is equal to 0, I is less than index, I plus plus, and we'll say cur node is equal to cur node get next node. That for loop is done, we'll return cur node. For outside of here, we're going to return null. Not a legal index. We can just say that's what we're going to do here, even though I think we saw either last class or a couple of classes ago that actually C++ does not require us to return a value. But I think it's good programming practice for programmers to say, look, I have advertised that I will return a node pointer. I don't have a node pointer I can return here. So at the very least, I'm going to give you a null value so that if anybody else tries to use it, it breaks. But we could certainly do a little bit more. And really, this is a type thing where we have some evidence of how our modern day exception handling was born. Because something like this is maybe a situation where we want to create an exception. So there's some sort of error message that's generated that could potentially be involved in a try catch, which didn't exist back then, to recover from a bad call or something. But for us, we can kind of assume that we're going to call this guy correctly and we'll get inside here all the time anyways, but at least this shows at least a little effort of error checking going on here. So don't discount that, but we're not bending over backwards to, add a whole bunch of extra checking in our program to, deal with things that you probably would deal with professionally if you were writing software for a company or something like that, needed to not crash horribly sometimes, that type of thing. All right, so get node at index. We're going to start off at the head. We'll spin through index number of times. Each time through, set cur node equal to his own next node. When we finally done that, we'll return the cur node. So this tool here now will give us a node at a specific index. This is going to be helpful for us, even though we can say under the hood it's going to be fairly inefficient. It's going to be helpful for us to be able to say, hey, give me the node that comes right before my current position. Right? I'm at bucket 3. I need the node that comes at bucket 2. I don't have the ability to get to the previous node, but I could just ask my list to give me bucket 2 and he'll hand me that node. We don't really care how much, how much running he's having to do to go and get this information under the hood.
I have a question.
Sure.
Would you see it as beneficial to also write something that gets the index of a node in the list?
Well, I guess I'm not going to say no. I mean, there certainly could be circumstances where we might be interested in, I'm trying to come up with, will it be related to anything we're doing here? I don't think so. But if you have a node, which effectively is I have a memory address, tell me where in the list this memory address lists, what index this memory address lives.
Yes, that's what I'm wondering.
Yeah. Well, I mean, so the answer is yes, there is probably some circumstance, some problem you'd be solving where that would be a helpful piece of information. I don't think that is helpful here. I don't think it's something we're going to need. But that doesn't mean there isn't some problem you might solve with a linked list where having the index of a memory address in your linked list might be a meaningful piece of information for you.
Okay, thank you.
And it's not like it's overly difficult to write. You take in a memory address, you start at the head and you keep walking through your list until you find a node that is actually equal to the node that was passed in. That is, the memory addresses are identical. Then you return the number of hops you took. So it's not an incredibly complex thing to write. It's just more a matter of, if you invent too many tools, but you only needed 3 of them, you might end up confusing yourself. So that's why I guess my kind of approach to programming has always been to let my program kind of organically grow, because I think there's always a danger of saying, oh, well, here's the 30 functions that I think I might need. And so you implement 30 functions and you now know how to do all sorts of stuff that you're never going to use, but you still don't know how to do the one thing you actually need. You know, there's all sorts of software products out there. Microsoft Excel is a good example. You know, you're looking at an evolved piece of software that's been around for a long time. I mean, nobody questions who is the king of the spreadsheet applications out there. Excel is the king of the spreadsheet applications because over the years, it has had so many things added to it for solving these very, 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 let's say, domain specific type problems that 99% of Excel users will never use, which then turns Excel into a tool that becomes somewhat difficult for probably a large percentage of their users because it knows how to do too much stuff. Most of the users will never use. Where let's call the Apple competitor with Excel is like Apple Numbers. Well, I mean, I use Numbers most of the time. I have both of them on my machine, but I'm not going to sit here and tell you that Numbers is the superior product to Excel. Because if we're looking at, you know, who's got the more magic tricks in their toolbox, Excel does by multiple times. You know, they're not even close to the same product when you just look at the number of magic tricks. But what Numbers does do well is they say, hey, here's the 4 things that you might do with a spreadsheet that most people might do with a spreadsheet. That's what we're offering you. So that's all you can do with this thing. And it makes Numbers fairly convenient to use for most things you might work with. So I like the approach of saying, hey, let's create our tool and evolve our functionality to match what we actually need, rather than try to guess at the features that we might need and then end up having too much stuff that we have to then fish through later. And the same thing is, I use the same approach in my software companies. When I still do it some, but when I used to run my software companies and I would sell software, I would try to talk clients into focusing on what they knew they needed rather than creating a requirements document. So this is something that's very related to those of you in this class who are currently in 370 software engineering. You know, one of the things that you focus in on there is the requirements document. And that requirements document is something that you work on with your with the client. Now, I promise you, you know more about computers than the client knows about computers, at least almost all of the time. The client has a product idea in their head, but they think that every function is trivial to implement. So they're going to say, oh, it needs to do this, it needs to do this, it needs to do this. Your job as a software engineer is to kind of, you know, cut through some of that crap and get to the core of it and say, what does it actually definitely need to do? Let's cover those things first. And, you know, that way you have the difference between the have to have features and the I would like to have features. Because more often than not, clients who are looking for software, they think they would like to have everything under the sun until they see the price tag. Or if you can start off lean, it's called a lean software development process. You can start off lean and say, hey, let's just build what we need, but we'll build it in such a way that we can bolt on expansions as we need to. Then when we bump into something that it doesn't do that you wanted to do, we can add that, rather than having looked at, oh, we've already spent a bunch of money on something and 3/4 of it we don't even need. So I like to keep things fairly lean and then add to it as we need to. So long-winded thing to your question, but it's a good, insightful question. And that's why I kind of went off on a thing with it, because it's very related to your whole industry. My opinion, so the short answer is yes, that might be helpful, but I don't think that feature is going to be helpful for us right now, or at least my mind's not taking me there. Maybe in a few minutes when we stumble across something, I might say, oh, I see where you're going with this. But right now, you know, my mind is, I don't know, 3 lines of code ahead, let's say. And I don't see a purpose for knowing the index of a memory address in the linked list yet. All right, but certainly this would be handy. because given the amount of times we're going to need to be traversing through our list, it would be pretty handy for us to just say, hey, look, I kind of need the pointer to the node at bucket 2 because I don't have a convenient way of getting there. And it doesn't matter that if I look at the actual implementation here, that this isn't even a convenient way of getting there. We're walking the whole list. But who cares? That's the computer's problem. We're the programmer. We ask for something, we get what we want. All right, so that's what this guy's job is. Okay, so there's our get node and index. So let's see, was I above or below that? All right, so we'll go ahead and get our current start. And then we want to also set our, let's see, do I want to go ahead and, I'm going to go ahead and get the node before as well. So I'm going to say node pointer, let's call this guy node before. And actually, you know what might be helpful here is I can probably make this mimic our traditional insertion sort the best if I actually just work with indexes rather than memory addresses and then rely on my function I just wrote to get me the actual nodes there. So what I'm going to actually go ahead and do is this. For int cur_start is equal to 1. That's the first bucket of my linked list that I'm going to be checking. Keep going as long as cur_start is less than this count. Let me, is it just this button? There we go. Cur_start plus plus. All right. We know this is going to look just like our array version of insertion sort. We're going to take cur_start on a voyage between bucket 1 and bucket count -1, just like we did before. Even though these things are strewn across memory all over the place. All right. So now what we want to do is, now that we're at a current start, we want to go ahead and we're going to use a couple of variables. Like I'll even good programming practice, even though modern compilers will let you get away with this, is if you're going to use some variables, go ahead and define them ahead of time and then give them values later. So I'm going to create a couple of node pointers. So I'm going to have a node pointer called cur_start node. I'll have follower node, and we'll call this guy the prev node. All right, so all those guys will be node pointers. Oh, can I not define them on the same line like that? I think you can, but I must be doing something stupid. I don't want to burn time on it. All right, so I defined a couple of nodes. This is going to be the actual node at cur_start node. This is going to be the actual node at the follower node. And actually, we might not even need this particular guy. In fact, I'm gonna cut him off right now. I don't think I'm going to need that particular node, but I am going to need the node I'm currently looking at. I'm going to need the node that comes right before him to possibly do my swap. I'll also need a node pointer. We'll call this guy a swap node. And then I'm going to need a couple of integers. So I'm going to need an int prevpos. Actually, let's call it the follower pause. That's the int I'm going to need there. Okay, so this is something that when we did this previously, iteratively, we would have done this. We would have used cur_start and the follower. Both of those guys were integers. They're still involved here. We're just going to use our extra function to do lookups. we're out at 11:20, right? So we got 3 minutes. Okay. So we're going to go ahead, and the very first thing we're going to do here is we're going to say the follower pause will get reset to the same thing as cur start. Every time through, the follower pause will get reset to the same thing as cur start. But now I need to go ahead and set up a couple of these things. So I need to say the follower node is equal to this get node at index, the follower pause. All right. So I'm keeping track of where I currently am in the list. So the follower starts off at the same place as cur start. But I'm also going to say, here's the node that that guy actually points to, because I'm going to need to compare things about that node to the things before this dude, which then also means that I need to be able to say the prev node is equal to, actually, do I want to put it inside a prev node yet? I don't. I'm actually not going to use prev node, and it's because you'll see the way the while loop is written. It's the same way the while loop was written when we had done this last year. So what we're really doing here next is we're asking, should I swap? Okay. And the condition in which we swap is this: while the follower pause is greater than 0. We are not at the first element of the list. And the follower node dot get payload, that value that I found there, is less than the dude that comes before my location, which will be this dot get node at index, the follower pause -1 get payload. All right, so if I'm not at the beginning of the list and the current payload I'm looking at is less than the payload at the dude before me, and I know there is a dude before me because I wouldn't even be in this and if this first part was false. So I must be at worst at bucket 1 or later in the list. So this says, get me the node at the bucket right before me, and then get me the payload of that guy. So I'm asking, is my current payload less than the payload before me? If it is, we need to do a swap between the follower node and the node before him. All right, that makes some sense? All right, so what I'm going to do for right now then, I'll make your, well, let's say your unofficial homework assignment for Tuesday to be to study for the exam and come with any questions things you want me to cover before your actual exam next Thursday. I'll finish this up on class on Thursday because now we're at the point where we just need to do the surgery to swap the nodes. So not a big deal, but also not something we want to rush through. We want to make sure we draw our pictures and don't lose anybody in space. But we shouldn't be much more than 5 or 10 minutes from finishing up our swaps here and having it done. But so for Tuesday, go back through our other material, practice some of the stuff, come with questions that you want to have clarified before the exam on Thursday, and we'll finish this up on Tuesday. I probably will not give you a homework assignment due on the day of the exam, but I might give you an assignment that will be due a week from Tuesday, so that it's something you could work on. You know, you can manage your own time to do it when you thought it was best, but since we won't actually meet next Thursday. All right, questions, comments, concerns, bribes? All right, I will see everybody on Tuesday.